We're now going to talk a bit about conditional probability, intersection, and independence. Now, conditional probability is the idea that we're going to find the probability of something happening given that something else has already occurred. We talked before about whether events are independent or not. So with a conditional probability, these would not be events that are independent of each other. And this is the way that it would be defined. We're going to have to find the probability of A and B over the probability of B, or if it's the case of the probability of B given A, then it's the probability of B intersected with A divided by the probability of A. And then we've talked about the product rule before, that you multiply together if you're wanting the probability that two things would occur. If you see an and, well, that's really what an intersection is. So if you're wanting for the probability of A intersected with B, that's the probability of A times the probability of B given A, or it's the probability of B times the probability of A given B. But this is the part that you want to make sure you pay attention to. Remember, we said there are times when the intersection set would actually not be a different value. I mean, it couldn't occur that you wouldn't have something that is both at the same time. So as long as they're independent, if they don't occur at the same time, then all you do is take the probability of A times the probability of B. That would be one way you could determine if events are independent, if the probability of A and B is the same as what you get when you multiply the probability of A times the probability of B. Now, here are some probabilities given to you for some sample space S, and we're going to read these probabilities out of the table. So, if we want the probability of C, that means we're going to go to where we see the column that says C, and we are going to come down to the total for C. That's 0.36. Because it would be 0.36 over 1. The total is 1. So it's just going to be 0.36. Now on 2, the probability of F isn't a column, it's a row. And the total over there is 0.15. And again, when you take 0.15 over 1, that's just 0.15. So both of these have been divided by 1. Now, if you look at 3, we want the probability of A intersected with F. In other words, we want the probability that something is in both A and F. And if I look in my table where A and F intersect, it's this value right here, 0.02. That's going to be my probability. Okay, what about C intersected with E? If you look in the table, see if you can find it. Give you a second to do that. Hopefully you've come up with 0.30. That's the probability of C intersected with E. Now, if we want the probability of A given F, then we have to remember that the probability of a conditional probability, A given F, means we go back to the table, and A given F would be A and F right here, the 0.02, but we have to take that and divide it by the probability of F, and the probability of F is 0.15. So if I divide that out, I get 0.133. And so the probability of F given A is very similar. We're going to find that F given A is where F and A intersect. Again, that's 0.02. But we divide it by the probability of A. Whatever is after the slash is got to be what the denominator is, and the probability of A was 0.07 because it's right here. And 0.02 divided by 0.07 is 0.286. Okay, the probability of D given E means we get the probability where D and E intersect. That's going to be this value in the table right here. So that is 0.35. And we've got to divide that by the probability of E. And if I look over here, my total for E, that's significant. That's 0.85. So if I take 0.35, divide it by 0.85, I get 0.412. All right, the probability of E given B. So I look in the table, here is where E and B intersect. So I'm going to have 0.1 on top, divided by the probability of B. And the probability of B is right here, 0.18. Simplify that, you end up with 0.556. And the probability of C given C, well, that means we have 0.36 divided by 0.36, and anything divided by itself is the number 1. Now, here's the question. Are events C and E independent? And why or why not? Now, here's what you're looking to see. We want to know if they're independent. Let me take you back up to the top so you can see this. They're independent if the probability of A intersected B would be the probability of A times B. That means on this, we want to see if the probability of C intersected with C is the same as the probability of C times the probability of E. So let's compare. The probability of C intersected with E, if I look in my table, is 0.30. If I were to compare that with the probability of C times the probability of E, well, the probability of C is 0.36, and the probability of E is 0.85. So if I were to multiply 0.36 times 0.85, let me do that real quickly. I'm going to come up with 0.306. That's very close. But the answer is no, they are not independent, and that is because the probability of C intersected with E does not equal the probability of C times the probability of E. That's the reason why they are not independent. Those two would have to be exactly the same. Now let's compare B and F. So if I were to take the probability of B intersected with F, that would end up being 0.08. Now, if I get the probability of B and I multiply it times the probability of F, the probability of B is 0.18, and we're going to multiply that times the probability of F is 0.15. So if I were to take 0.18 times 0.15, I get 0.027. So are these independent? The answer is no. And that's for the same reason. The probability of B intersected with F does not equal the probability of B times the probability of F. So that's an important test to remember. Let's go to the next slide. Okay, 2 balls are drawn from a container that holds 5 red balls, 7 green balls, 8 white balls. This may sound familiar because we have looked at a question similar to this before, but now look at what it says. We're going to draw the first ball and we're going to replace it before the second ball is drawn, and we want to find these probabilities. So the probability that both balls are green, I need the probability of a green times the probability of a green. Now I do need to ask myself, are these independent? And the answer to that one is yes, because if as long as I put that ball back after I draw it the first time, my probability of drawing the ball on the second draw has not changed from what it was on the first draw. If I didn't replace it, it would not be independent, but these are going to be independent. So the fact that I'm replacing it means I have 7 out of 20 balls that are green. When I put it back and I draw again, I still have a 7 out of 20 chance of getting a green ball. If I multiply those probabilities together, then I'm going to come up with 49 over 400, which is about 0.1225. It's a little over a 12% chance that that would happen. Now, the probability that neither ball is green, I could think of it this way. I want the probability that it's not green times the probability that it's not green. Okay? Now, since the probability of it being green was 7 out of 20, that means it's 13 out of 20 chance that it won't be green. And that would be the same probability on the second draw. So if I do 13 over 20 times 13 over 20, that's 169 over 400, which gives me a little over 42%, 0.4225 as my probability. Now, this one you're going to have to think a bit. I want the probability that at least one ball is green. Here's what that's saying. I could either draw in 1 ball is green, or I could draw in 2 balls are green. Now, I can calculate those probabilities individually, or the easier way is to have 1 minus the probability that I get no green, because that is easier to compute. Okay? In fact, did I just calculate the probability that I don't get a green ball, that neither one is green? Yes. So all I have to do is 1 minus 0.4225, take my answer from B. Using the complement, I get 0.5775. That's the probability that at least one ball would be green. That would mean it's okay if 1 is green or 2 is green. It's just everything except getting no green. Now, in part B, it says if the first ball drawn is not replaced before the second ball is drawn, we're going to have to recalculate these probabilities. Same question. I want the probability both balls are green, but here's what happened on that first draw. I get 7 out of 20 because there were 7 green out of 20 balls, but I don't put it back. So when I go to draw the second ball, there are only how many balls left to draw from? There's not 20 anymore. There's only 19. And if I already drew a green one, instead of 7 green ones being in there, how many green ones are in there now? 6. So if I were to multiply 7 over 20 times 6 over 19, I'm going to come up with, I could do a little reducing. 2 goes into 6 3 times. 2 goes into 20 10 times. And I get 21 over 190, which is 0.1105. That probability has now changed. How about the probability that neither ball is green? Now, we did that one earlier too, but instead of 13 over 20 times 13 over 20, here's the probability the first one is not green. But now, again, when I go back to draw, if I didn't put that one back, I only have 19 balls left to draw from, and that would mean how many of what remain would not be green. Well, there were 13. I've taken one out. Now there's only 12 in there that are not green. So again, if I do a little reducing, I can divide 4 into 12 3 times. 4 goes into 25 times. That's going to give me 39 over 95, which is 0.4105. So a little over a 41% likelihood that neither one would be green. And again, I can calculate that at least one ball is green the same way. I can get the complement. That would be 1 minus the probability of no green, which we just found in B. So 1 minus 0.4105 would give us 0.5895. And let's look at the last slide. Okay, we have a table. And this is for a study to determine the frequency and dependency of left-handedness relative to females and males. So 1,000 people were chosen at random, and here are the results. So we had a total of 440 females, looking at this column. We had 560 males for a total of 1,000 people. Here's how many were left-handed. Here's how many were right-handed. And then it's also broken down according to males and females. So if we were to convert this to a probability table, we could take the number that we see, for instance, right here, where we had 52 left-handed females, divided by 1,000. That gives us 0.052. That's the probability that a female would be left-handed. And so we've calculated that for all of these values. And the question is, what's the probability that a person chosen at random is left-handed? Well, I want to look for the row that says left-handed, and when I get to the total, that's all I need. 0.13 is the probability that a person chosen at random would be left-handed. Now, what's the probability that a person chosen at random is a left-handed woman? Well, a left-handed woman is going to be a left-handed female, and that's this right here, 0.052. Not a very high probability. You'll notice it's much more likely for a male to be left-handed than for a female. Now, look at D. This says, what's the probability that a person is a woman, that a person is female, given that the person is left-handed? Okay, now I'm going to write that out using the probability notation so we can pay attention to how we need to set this up. So if I want the probability that a person is female, given that the person is left-handed, remember I need to find what would be the number of left-handed females. And we just saw that from C. That was 0.052. But I have been given that the person is left-handed. That means I have to put that over the total number of left-handed people, or the probability of, out of that 1,000, how many would have been left-handed. And that's 0.130. Now, if I calculate that, I come up with 0.4. Okay? There's only a 40% chance that, given that somebody is left-handed, that it would actually end up being a woman. Okay? Let's look at the next one. What is the probability that a person is left-handed given that the person is a male? So that means I need to go to the table, get the probability of being left-handed and male, and that looks like that is 0.078. But I need to divide that by the probability of being male. And according to our table, we had 0.560 that were male. So that gives us 0.139. Okay? So if I'm just looking at the males, the probability that a male would be left-handed is going to be 0.139. Now the question is, Are the events left-handedness and male independent? Well, and again, we're answering the question why or why not. So what I need to find out is the probability of being left hand and male the same as the probability of being left-handed times the probability of being male? Now, looking at the table, the probability of being left-handed and male, okay, was right here, the 0.078. So let's write that down. And then we'll see what we get when we multiply the probability of being left-handed times the probability of being male. So the probability of being left-handed was 0.130, and the probability of being male was 0.560. So we're going to have 0.130 times 0.560. And if we multiply that out, we find out, give me just a second, and I'm going to put this in my calculator. So we had 0.130 times 0.560, and I've got 0.0728, which is not the same thing as 0.078. So what that tells us is because they are not the same, they are not independent. Okay? Since the probability of being left-handed intersected with being male does not equal the probability of being left-handed times the probability of being male, they are not independent.